This video is to explain Lesson 7-4, which some people missed due to SAT prep, etc. So the purpose of this lesson is to learn to find a confidence interval for a population mean if we do not know the standard deviation. We've learned how to find it for a population proportion or percentage, and also to find it with the population mean if we did know the standard deviation, that sigma that you see there. But now this time we are not going to have that. So the situation is that if we do not know the population standard deviation, that sigma there, then we're going to estimate it with the sample standard deviation, which is this S value. Since we do not know the standard deviation of the population, we can't use what we've been doing so far, where we would use a normal distribution that has like a z-score in it. So before our formula is going to have to change a little bit. So instead of using the normal z distribution, we're going to have to introduce you a new one called the student t-distribution. I will just call it a t-distribution. That's normally how it is called, as people often don't drop the word student with it. But that's going to then once again use our sample standard deviation, that S, of instead of that sigma. It is also accurate that the sample standard deviation is more accurate the bigger your sample size is. So that's kind of important to note as well. It is based off of something called the degrees of freedom. Degrees of freedom, it says the number of degrees of freedom for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed. So for example, what you really need to know is, hey, degrees of freedom is my n minus 1. N is your sample size. So in an example in just a few moments, you are going to be asked to find a 95% confidence interval, and your n is 20. So my degrees of freedom would be 20 minus 1, or 19. So what we're going to do then is find it in two different ways. But let me quickly explain degrees of freedom a little bit more. A lot of you guys know what a mean represents, and so you find, like, I'm going to do a mean of sample size of 4. So for example, I could add in 4 values, 1, 2, 3, 4, and then I would have to divide that all by 4, and that's going to give me my sample mean of 5. So right now my certain restriction is that my mean has to equal 5. So then what I can do is I can vary. I can pick any number I want for this first number. Like whatever this data value is, let's say it is the 6. And then my next value can be whatever I want it to be. Let's say it's a 10. And then the next number, it can be whatever I want it to be. And let's say it is a 3. Now that I've picked those values, or I've gathered those values, whatever, now this last one, I don't have a choice anymore. All right, it can't vary anymore, because if I used algebra and put this as x, I could solve for x, and there would only be one value for x. So there's no wiggle room on what x is going to be. X has got to be this number to get me my mean of 5. However, if you notice on this one, with my sample size of 4, my degrees of freedom would have been 4 minus 1, or 3. And see this, these are the 3 numbers that could have varied, right? I had the freedom to pick whatever I wanted for these 3 numbers, and so that's those 3 numbers. But after those 3 numbers are picked, then I don't have choice anymore. So that's why my degrees of freedom is 3. Those are the sample values that can vary after I restricted that my mean has to equal 5. Once again, you don't really need to know like how to explain this degrees of freedom idea. You need to know this part right here, this formula that's n minus 1. All right, so to find a student t-distribution, or t-distribution, this formula that you see right here is going to not really be used in this unit, but I just want to compare it to what you've seen before, a z distribution, where you had x bar minus your population mean divided by your standard deviation of your population over the square root of n. So the only two things that are going to change right here is your t is going to change and your s is going to change. So hey, instead of a z, now I have a t. Instead of my population standard deviation, I have to use my sample standard deviation. Those are the only things that are kind of changing in this situation, but that makes us use this whole new distribution of a t distribution. So how do I find a critical value for a t distribution? And that's why we need to find that, is because I'm going to quick this with a table and the other is with a calculator. I need to go over the table way because the table way, or excuse me, some people's calculator doesn't offer this feature, so some people have to use the table. So I want to make sure everybody knows what to do. So this t distribution table, it's looks something like this. There, then you need to always round down to the closest one that isn't on the table. So if my degrees of freedom was 53, then I'm going to round down and I'm going to use 50. Let's say my degrees of freedom was 59. I'm still going to round down and go with 50. Even though it's closer to 60, I need to be careful in that regard. And so, forward a second. There's two ways to find it. And I've cut it off so I can fit this all in. So this keeps going down further, and these are the degrees of freedom. And the key thing is that after, I think, 40 on the table, it starts to jump. So it goes like 40, 45, 50, then it maybe goes 50, 60, 70, 80, and even like 100, then 200, like it jumps around. So if you have a degrees of freedom of 53, then that's so 54 minus 1, so 53. That's not on, it's going to not be on here. So the rule is that instead go to the example that we're going to need in a second. The example we're going to need in a second is that we're going to create a 95% confidence interval, and we want to have a sample size as 20. So once again, our degrees of freedom is going to be 19. 20 minus 1 is 19. So I'm going to go on my degrees of freedom column, and I'm going to find the 19. And then here the thing is 95% confidence interval means that I have 5% left over in my two tails. So I'm going to always look at the area of two tails here. And so I want the 0.05 there for a 95% confidence interval. And then I just look for the intersection and I find this number right here. So that's going to be our critical value that we're going to use in a future problem. So I can also get this exact same number here on my calculator. And why this is because the table, once again, you're going to have to start jumping with bigger degrees of freedom. You don't have the exact number and have to round down. The calculator, you wouldn't have to round at all. It will give you the exact value you needed. So I have a 95% confidence interval. So that means that in the middle value, I have 95% of my data. So I'm going to have 0.025 left over in each tail. So that 5% total is in the tails. And so this is the value that you're looking for right here. This is my critical value. Oops, that does not look like a alpha there. Oops, divided by 2. So this is always the upper value that you want. So you want to find the area to the left of that. So that's all the way down this direction. And so if I added 0.95 plus that tail right here, my area to the left is going to be 0.975. My degrees of freedom, if you recall, was 19 because it was 20 was our sample size minus 1. So I'm going to do inverse t of that value. And I'm going to get the same number I just get on the table because, once again, the table I didn't have to do any rounding on. So jump back again in just a second on an example. So we're going to create one confidence interval when we do not know our sample standard we do not know our population standard deviation. But just like before, you have to check some requirements that, hey, this is accurate, I can do this, these procedures. So the first one is that it is a simple random sample. And then we do not know this, so you don't have to check that that's known like it was with the population mean example. Excuse me, the sample standard deviation when I know my population standard deviation. Explain, either of both of these conditions must be true. The sample is either normally distributed or the population is great enough that central limit theorem says we can do it. Those are our two requirements, okay? a lot. All right, the reason I need to find a critical t-value is because you've seen this formula before. This formula is for finding a confidence interval. You take your sample mean minus your margin of error and your sample mean plus your margin of error. But the key thing here is that my margin of error changes. I need the critical t-value instead of a z critical value, and I'm finding my sample standard deviation instead of my population standard deviation. So that's kind of why we need to get this critical value. So then after that, you're going to create the confidence interval using the same formula that we just talked about. Those two are the things that have changed. And so here's our example. It shows everything out right now, but let's kind of walk through some of this a moment. So it says it's a simple random sample, so that's stated, and it says from a normal population, so stated, perfect. For hospital costs for crash victims who wear seatbelts, N is 20, my sample mean is 9,004, my S, my sample standard deviation is 569. Find a 95% confidence interval. So after I got my two things checked, it's helpful if you're doing this kind of by hand to first find E. So once again, that was that. E was our critical value times sample size, or sample standard deviation divided by our square root of our sample size. So that critical value you can see is right here. And then my sample standard deviation is right here. And then, oops, sorry, I just wrote over it. And then my square root of n, 20. So I just calculate that and get this number for my margin of error. So then you're going to do your x bar minus that and your x bar plus that. So that's the 9,000 minus that number and the 9,004 plus that number to get this being our confidence interval. And then when we interpret it, we do the exact way we were doing before. We're 95% confident that. And if you look carefully, that phrasing that you might want, because you have to put it in context of the problem, is often in the problem that it gave me. So it said here, hey, hospital costs for crash victims who wore seatbelts. So, hey, the true mean for hospital costs for car crashes, I could technically add that wore seatbelts, is between these two values right here, which is what you got from your confidence interval. Your calculator as well to get that same interval. The problem with using your calculator is that it won't go back and give you what this actual value was. It'll give you the interval that you get kind of in that format, but it doesn't give you what they did that. You can use algebra to get that, but it's not necessary either. It's stat test t interval, just the same location that you find the z interval in the one prop z interval or int. So often you're going to highlight the stats. In this last problem, you would have highlighted the stats like, hey, I'm given just my sample mean, my sample standard deviation, my sample size, and my confidence level. So I can enter those in. The other option, once again, is data. And data is when you're actually given a list of numbers. And so you'd want to put that data in list 1 or list 2 or whatever. And then you don't have to do anything else but put the data in your list, highlight the data, and give your C level and press calculate. And it will give you then the sample mean, the sample standard deviation. So I don't need to go back through and say, hey, go and calculate out one var stats to get the sample mean standard deviation. It will give it to you when you calculate that t interval using data option. In this case, we don't need that. We just need the stats option. So I'm going to close the slide where it kind of has one last example. Excuse me. So you could go ahead and do this example if you wanted to and try it again on your own. The only thing I didn't really like about this one is that it says, as for the SRS, it says yes stated. That's actually not true. I don't see anywhere in here where it does say it is. They are testing the effects of garlic, and it looks like that they're doing some kind of a experiment with that. So possibly that you'd hope they'd use randomization, etc., but it's not fully clear and it's not deliberately stated here. And so that's something you want to be looking for. And the last thing is it's the change is in then their levels. So we don't know when they did the change. See how I get some positive and negative numbers on this one? Oops. When I get the positive and negative numbers, like is the change that I took the before minus the after or the after minus the before? So it was a negative number really, see I kind of explain it right here. It's not clear if a positive number means that the LDL cholesterol level increased or decreased because I don't know which way that was subtracted. So that's kind of a negative flaw in the description that they give here. All right, so hopefully that explains everything to you. Please feel free to email me with questions or set up an office